Welcome viewers to the second segment of the first lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous segment, we stated and proved a very useful lemma that is going to be proved handy um, as we move along throughout the first lecture. Okay, so it's time to state the first theorem of this lecture. Let me state it first and then I'll prove it. Theorem 1, which concerns the homology groups of two torus. Let T denote the complex represented by the labeled complex by the labeled rectangle L of the following figure. Okay, so let me draw it now. The label rectangle that I'm going to use for a while. So let me erase everything. So I'm going to draw this rectangle, labeled rectangle now. I want to put it in such a way that I can write without erasing this figure. Okay, so let me draw it a little. I think it's better to draw it here. So here is the rectangle. Now I need to divide it into the length into 3 equal parts. I'm going to do the same with the width. Okay. A, B, C, A. So the labeling indicates that this vertex is going to be identified with that vertex here along the top edge of this rectangle, and then along the left edge it's going to be A, D, E, and A again. Okay, and then along the bottom edge it's going to be A, B, C, A, and along the right edge is going to be A, D, E, A. Okay, so I'm going to denote the top edge of this complex L of the rectangle L by S. This is the top edge of rectangle, top edge of the rectangle, and the left edge of the rectangle is going to be denoted by R. The left edge of L. Okay, now Okay, so the labeling suggests how we are going to glue this complex. So, you know, these two vertices are labeled by the same letter A, means that this vertex is going to be identified with this vertex, and this is also labeled by A. This vertex is also labeled by A. So there are three vertices labeled by the same letter A, meaning that they are all going to be identified. And D is here and D is here as well, which means that these two vertices are going to be identified. E is here as well. So which essentially means, which actually means that this top edge is going to be identified with the bottom edge, and the left edge is going to be identified with the right edge of the underlying rectangle. And you know, this is the gluing or the pasting map, and under the action of this pasting map we get the two torus. Let me draw these two torus. This is the two torus that we have, and here is a circle. Okay. And here is another circle. So this circle we denote by this is actually this circle is G of mod R. Okay, so mod R is the underlying space of the left edge of the complex L. Okay, and after we apply the pasting map, we have this circle. Okay, and this guy is G of the underlying space of the top edge of the rectangle, G of mod S. Okay, so figure 5 tells us how we obtain a two torus by applying this gluing map G. So let me name this figure 5 as two torus. Okay, so this is the relevant diagram. So a short note here, top edge, or equivalently the bottom edge of the label complex labeled complex. This is the label complex L. Label complex L is denoted by S, this one, and the left edge or equivalently the right edge, the right edge of the label complex L L is denoted by R. Okay. All right. So now, here is the label complex on the left of the figure, and label complex L on the left of the figure, and the underlying space of this label complex. So once we have this labeling, it means that we are applying the, you know, the gluing map automatically, because the labeling suggests that the gluing applies. Okay, so the underlying space of the label complex L is the torus. The underlying space of the labeled complex L is the torus. Okay, then the first homology group of the torus T is isomorphic to two copies of Z. Okay, or Z direct sum Z, and the second homology group of the two torus is isomorphic to simply Z. So it turns out that both the homology groups of T, the first homology group and the second homology group, they are both free abelian. Okay, now orient each two simplex of L counterclockwise. All right, which means that this goes counterclockwise, this also goes counterclockwise. Each of the two simplices here is oriented counterclockwise. All right. So use the induced orientation. Use the induced orientation of the two simplices on this torus T. On T, let gamma be their sum. That is, gamma is equal to sum of sigma I, where I runs over a finite set. Let W1 is equal to these one chains. W1 is a one chain, which is the sum of the following elementary one chains: AB plus BC plus CA, and Z1 be the one chain given by AD, A comma D, plus D comma E, plus E comma A, given by equation number 7 and 8 respectively. then gamma generates H2 of T. All right, and W1 and Z1 represent a basis for H1 of T. This is the statement of the theorem 3, which concerns the first homology group and the second homology group of two torus. Okay. Okay. So now it's time to prove theorem 1. So let me keep the figure 5 intact and erase the writing here. Okay, so here goes the proof. Let us focus on the gluing map here. G, well, here is the underlying space L, underlying space of L, okay, which is a rectangle, right? I think in the statement of theorem 1 I mixed up with the underlying space of this complex L with the underlying space of the complex T. They're not the same actually, they are different. I say in the statement I mentioned that the underlying space of the label complex L is a torus, which is not actually fully correct, because the underlying space of the label complex L is the rectangle here, labeled rectangle on the left, and underlying space of the complex T is the torus, which is denoted by mod T, which is a topological space, so is mod L, and G is the gluing map from one topological space to the other topological space, mod L to mod T. Okay, and let this be the underlying gluing map also let A be the image of the underlying space of the boundary of the rectangle, image. So let A be the image of the underlying space of the boundary of the rectangle under the gluing map G. Okay, so that A is definitely a subspace of the topological space mod T. All right, this guy. So one can immediately see that this boundary. So I'm going to take this boundary, and when I do the identification under the gluing map, so this edge is going to be identified with this edge, and this edge is going to be identified with this edge, so that what the boundary is going to be mapped to the wedge sum of two circles here on the right, in the two torus, on the two torus. So this is homeomorphic to a space that is the union of two circles with a point in common, with a point in common. Such a union or such a space is called the weight sum of two circles. Is called the weight sum of two circles. Weight sum of two circles. Okay, so we see that this space A, the subspace of the torus A, the torus T, the mod T, the underlying space of the complex T, which is the torus. This subspace is homeomorphic to the weight sum of two circles. In the figure, this is one of the circles, and this is the other circle. Okay. All right. Now we have the freedom of choosing the orientation of the one simplices of T arbitrarily. So let me write it here. Orient the one simplices arbitrarily Now, it's important to know that you need to convince yourself that the arguments that we applied to prove lemma 1 also applies here. Since the gluing followed by the map G, followed by the map G, okay, only take place along the boundary BDL. Map G only takes place along BDL. Okay, so I need to draw a picture here. So it's better if I erase this donut here and try to draw another torus, illustrating the fact that all these two simplices stay intact under the identification. All the orientations stay intact. None of them is disrupted under the gluing map. Let me show you in this picture. Let me draw the torus, a bigger torus. This point is A, this vertex is A, this vertex is this is D, and it should be E. Okay, and the orientations stay the same. All the orientations stay the same. Okay. So that you can actually, so all the other two simplices are placed here exactly the same way they are placed here in this labeled complex L. Okay, so all the arguments that were presented in lemma 1 actually hold here as well in the case of two torus. Okay, so the figure tells us how to form the complex T from the complex L using the gluing map G. The simplices of T here, these simplices, behave exactly the same as those of this label complex L under such identification, so that lemma 1 applies. All right, so in the notes it's written clearly in the caption of this figure. Okay, so since lemma 1 applies, the first statement of lemma 1 tells us that every one cycle of T is homologous to a one cycle carried by the wedge of these two circles, meaning A, carried by A. Okay. All right. So that's the first statement of lemma 1. And the second statement, if we apply the second statement for the case of two torus, we get the following. If D is a two chain of T, and if delta 2D is carried by A equal to G of mod of boundary of L, then D is a multiple of, we already stated in Theorem 1 what gamma is, right? Then D is a multiple of gamma, which is the sum of all the two underlying two simplices. Okay, so in addition to these two results, we have two more results to state in the case of these two torus. What are those? 3. If C is a one cycle of T carried by A, then C is of the form NW1 plus MZ1, where both N and M are integers. Okay, and for del Q gamma is 0. Okay, which means gamma is a 2 cycle. Good. So we are going to prove 3 and 4. Okay, we have to prove that they hold. So so it's simple. So what is A in our case? In our case, A is the wage sum of two circles, and what a circle is just the boundary of two simplex, right? Circle is the boundary of a two simplex. Okay, and so the two circles involved are the boundaries of two simplices, right? So let me draw two simplices here, which join at the point A. Okay, this is the point A where these two circles meet. So this is one circle, and this is the other circle. This is the other side of the circle. This is the other circle, and they meet at the point A. So so this is one circle, ABC. So which we can write as the boundary, which we can draw as the boundary of this two simplex ABC, and the other one being AED or ADE, right? This one. Okay, and starting from A we go to E, and then coming back to A via DA. Okay, so this figure tells us that this is the boundary. A is equal to the image of the underlying space of boundary of L under the under the gluing map G. So all right, I need some space, so let me erase something from this side. Okay, so let C be one cycle carried by the complex given in this figure 6. By this is nothing but A, right? Carried by the complex given in figure 6. Okay. So let us write it. C is equal to N1 A comma B plus N2 B comma C plus N3 C comma A plus N4 A comma E plus N5 E comma D plus N6 D comma A, right? So this is the generic expression of this one cycle carried by this complex given in figure 6. Okay, so since C is a one cycle, we want delta 1 C, which is from this expression can be computed as n1 b minus a plus n2 c minus b plus n3 a minus c plus n4 e minus a plus n5 d minus e plus n6 a minus d, okay, which can be rearranged to look like as n minus n2 n1 minus n2 times b plus n6 minus n1 plus n3 minus n4 times a plus n2 minus n3 times c plus n5 minus n6 times d plus n4 minus n5 times e, and since c is a one cycle, delta 1 s since c is a one cycle, delta 1 c must be equal to 0, and it is equal to 0 means we have the following equations: n1 is equal to n2, n6 is equal to n1 plus n4 minus n3, and we also have n2 to be equal to n3, n5 is equal to n6, and n4 is equal to n5. And if we apply these things here, then we get that n6 is equal to n2 plus n5 minus n2, which means n6 is equal to n5, which is exactly this equation. So we group these equations and number it as equation number 10. Good. So now we are going to use this equation 10 in this expression of C and see how C looks. Okay, and we immediately, so let me erase everything here and see that C looks like this. So since n1, n2 and n3, they are all equal, we can factor out n1 from these three expressions, three elementary one chains. So n1 is the coefficient of all three one chains, a comma b, b comma c, and c comma a. C comma a, and n4 can similarly be factored out from the sum of the three elementary one chains, which are AE, ED, and DA. Okay, so we leave n1 as it is, and we manipulate the second command, and we put a minus here, and negate the orientations of all these put a minus sign in front of all these elementary one chains, so that a comma e becomes e comma a, and e comma d becomes d comma e, and d comma a becomes a comma d, okay, with an extra minus sign in front. And this reads as NW1 plus MZ1, where I have taken N1 to be equal to N, and we use the notation M to be equal to minus N4, okay, where M and N are integers. Okay, so this is how we prove result 3 for the case of two torus. Now we need to prove 4. Okay, let me erase everything here. Okay. So this figure, we are going to use this figure again. So let us prove 4, and gamma here is nothing but sum of sigma i's. Okay, so the sigma i's here are actually the same as the sigma i's here that we have already discussed. Okay, so it doesn't matter which picture I choose to describe them, they're identical. And we already have mentioned that these sigma i's are oriented counterclockwise, right? Now, what is the okay, I think I'm going to label this vertex by F and this guy by H, okay, because I'm going to explicitly compute the boundary of and also I'm going to call it sigma 1 and call this sigma 2. Okay, so what is delta 2 sigma 1 in this case? It's going to be so we're taking this 2 simplex, and the boundary of this 2 simplex is going to be equal to B comma A plus A comma F plus F comma B. Okay, these are all elementary one chains. All right, this is our equation number 11. And similarly, one can find delta 2 sigma 2, which is A comma B plus B comma H plus H comma A. This is equation number 12. So this is nothing but minus B comma A plus B comma H plus H comma A. Okay, I'm sorry, this is going to be called equation number 12. All right, so we immediately see that this guy, when you add them up, this does not have any contribution of the one chain B comma A, because this is going to be cancelled against this contribution. So there is no contribution of B comma A here, right? So what does it mean? It means that when we try to compute del 2 gamma, which is nothing but sum of all the expressions like del 2 sigma I, it is going to be 0 on the one simplex, this is 0 on the one simplex a comma b, right? So for all the one simplices not belonging to the boundary of L, so this is something that we checked for for something for the one simplex AB that belongs to the boundary of L, right? One can similarly see that for any other simplex, for any other one simplex that does not belong to the boundary of L, one can explicitly check that for such a one simplex, delta 2 gamma is going to be 0 on that one simplex if that one simplex does not belong to the boundary of L. Say we can choose this one simplex, right, which does not belong to this boundary of the rectangle, right? And we can check, in that case we have to take these two simplices and do the same computations that we did here with sigma 1 and sigma 2, and we'll see that that if we take these two simplices, then when we apply the the boundary operators on the respective elementary two chains, okay, then and then add them up, and then we'll see that there will be no contribution in the resulting expression. There will be no contribution of this one simplex in the resulting expression. They will be cancelled. So in both the expression of so these are two simplices, and we will work with the elementary two chains corresponding to these two simplices when the boundary operator acts on one in both on both these elementary two chains. There will be contributions of this one simplex in each of those expressions, but one will be the negative of the other, and when you add them up, the resulting contribution will be 0. That's what I'm saying. Okay, and similarly you can check for any other one simplex that does not belong to the boundary of L, for which you will see that delta 2 gamma is going to be 0 for those one simplices. Delta 2 gamma is going to be 0 on those one simplices that don't belong to the boundary of the complex L. Okay, good. And for all the one simplices belonging to the boundary, we have already we at least checked for one of them, like AB. Similarly, one can check for BC. For BC, when we take BC, we have to take this simplex, this two simplex and this two simplex, and do the same thing that we have done here. Okay. All right. Okay. So we also verified that delta 2 gamma is 0. Okay. It is 0 on all the one simplices that we are dealing with, be it in the be it on the boundary, or be it even if it does not belong to the boundary, delta 2 gamma is going to be 0 on that one simplex. Okay, so now using these four facts, we are going to compute the homology groups of the two torus. Okay. Okay. Given a one cycle C of T by 1, okay, remember 1, which states that every one cycle of T is carried by A, which is the wedge sum of two circles, right? That was given by result 1. Sorry, every one cycle of T, yeah, it's the same. Every one cycle of T is homologous to a one cycle carried by A. That's the first statement. So given a one cycle C of T by 1, C is carried by A, or C is homologous to a one cycle that is carried by A. But we can, we can express it by saying it directly that C is carried by A. By 3, which states that if C is a one cycle of T carried by A, then C is of the form NW1 plus MZ1, right? Now by 3, the one cycle that we started with is equal to NW1 plus MZ1 for some NM in the set of integers. Now such a cycle bounds if there exists a two chain, right? There exists a two chain D of the torus T satisfying C equal to del 2D, and in that case we say that this one cycle C bounds, right? Right. Now we know that the one cycle C that we started with is carried by A, which is the wedge sum of the two circles, right? Since C is carried by A, del 2D is also carried by A, right? So you see the del 2D is carried by A, right? Now, number 2, result number 2 tells us that if D is a two chain, which in our case is, right, D is a two chain of T, and if del 2D is carried by A, then D is a multiple of gamma. So in our case, we conclude that D is equal to, so since this is the case, result 2 tells us that D is equal to P gamma for some P belonging to the set of integers. Now, C is equal to del 2D and D is equal to P gamma. Therefore, del 2 P gamma, right, which is equal to P del 2 gamma, and by 4, del 2 gamma is 0, right? So P times 0 is 0, and this we get by 4. So which means that we thus find that the one cycle C bounds implies that C is trivial, or in other words, C is equal to 0, right? So what does that mean? It means that the boundary B, the one boundary of the complex T, is trivial, while we have seen that a one cycle C is written as N1W plus, NW1 plus MZ1, where N, M are both integers, right? So we have seen that Z1 of T, the group of one cycles, is nothing but two copies of Z, or Z direct sum Z. Hence, we conclude that the first homology group of the complex T, which is nothing but Z1T modded out by B1T, B1 of T, is isomorphic to Z direct sum Z. Okay. And so since the one cycle, any one cycle, is written as NW1 plus MZ1, the one cycles W1 and Z1 form a basis of the free abelian group H1 of T. Okay, no torsion present here for the case of two torus. This group is written, it's a free abelian group which is Z plus Z, and it's generated by these two one cycles, W1 and Z1. Okay, let us compute H2 of T, which is the second homology group of the two torus. Let D be a two cycle on T, then since it's a two cycle, del 2D is equal to 0, right? Okay, so we have gotten del 2D is equal to 0. Since del 2D is 0, so del 2D is equal to 0. What does that mean? It means that del 2D is 0 on every one simplex that is not in G of mod of boundary of L. Okay. Since we are dealing with torus, we have to deal with this thing, right? Since del 2D is 0 everywhere actually, and which means that del 2D is of course 0 on every one simplex that is not in here. Okay, we conclude that del 2D is trivially carried by the boundary G of mod of boundary of L, okay, which is the weight sum of the two circles A. Hence now, so since this is the case, 2 applies, right? So we started with so we have a 2 chain, and del 2 of D is carried by A, and hence 2 applies, and 2 tells us that D is equal to P times gamma for some integer P with P belonging to the set of integers, or by means of result 2 we arrive at here. So so every 2 cycle is written this way, right? Which means that this the group of 2 cycles for the torus is nothing but set, the group of integers or the set of integers, right? Okay, now this is good. Now there are no 3 chains, or no 3 chains in this case, and hence the domain of the map is trivial. The domain of this map is trivial. This guy is trivial. What does that mean? Since it's a homomorphism, del 3 is a group homomorphism. So the image of this guy here has to be trivial as well. The image of del 3 has to be trivial in C2 of T, right? What does that mean? The image of this boundary map is precisely B2 of T, right? B2 of T is trivial. What does that mean? It means that the 2 cycle D that bounds is just 0. Okay. Okay, what does that mean? It means that, Z2 of T modded out by B2 of T is nothing but isomorphic to simply Z. So which proves that, so this guy is H2 of T. So the second homology group of 2 torus is isomorphic to Z, the additive group of integers, QED. Okay, so we have thus seen that the first homology group of the 2 torus is isomorphic to Z direction Z, and the second homology group of the 2 torus is isomorphic to Z. Both of them are free abelian groups. There is no torsion component. Okay, all right. QED. So this is the first theorem. So I'll take a break and we'll be back with the second theorem, which will give us the results for homology groups for Klein bottle. Thank you for attending this second segment.